So here we have our typical stand. It's kind of a mixed wood stand on the Roman forest. We have our basic stand level information about our species composition, that darn thing called age, height, stalking, site quality, and size. So now what we're able to do is actually look at the variation. In this case, this is quadratic mean diameter. So how's that diameter vary across the stand? So now I have that measure. And I can also calculate the stats, so it's basically 19.5 plus or minus 0.5 centimeters for that stand. I can also get that same impression for biomass or gross vegetable volume or height. Another interesting thing that we've been had the benefit of working with is we're very plugged into Queen's University. And Paul Trites and his PhD students, his master students, and one of their students, Dr. Van has come up with this vertical complexity index, which basically is a statistic between 0 and 1 that reflects forest structure. So what we've learned, and it sort of is a forest type dependent number. It's not, it doesn't, the number thresholds don't mean the same for every single species. But if you have a vertical complexity index around 0.1, you're basically that single layer condition. If you have something around 0.3, you have sort of two-tier stand situation. So you have one low, regeneration, cohort underneath, and an overstory. Once you get up numbers about 0.7, it basically indicates you have a complex forest structure. Now, this piece of information has allowed us to do some very interesting things. One of them is try to take that list of inventory metrics we had, volume, basal area, and quadratic mean diameter, because I have industry knocking my door saying, yeah, that diameter piece, that's excellent. That mean tree volume piece, that's pretty good. But how many 12 centimeter trees am I going to have there? What volume in my 30 centimeter class am I going to have? Well, we've been able to work and actually develop size class distribution models, again, from the point cloud data. So what this is validation plots. I'm not trying to snow you at all. This is a result of looking at grouping our validation data set by those vertical complexity classes. So say, okay, let me look at model a prediction of where I have single story stands. So that first example is, boy, this is getting old, reading glasses is pain. So we're looking here at having low vertical complexity index numbers on the left-hand side, and it basically goes down here. So you can see we kind of have this inverse J shape, and then we're slowly moving towards normalization. So the blue lines are the plot data. The red line is the predicted model results for those plots in that situation. So we were pretty impressed that we were able to get that. Now, black spruce distributions, they're pretty nice, they're pretty normal generally. When you get to mixed woods, the models are working reasonably well. We actually have a couple different model cores that we use, and we use the vertical complexity index to tell us which type of model to apply to the different stand conditions. But all of a sudden, we're able to now animate our inventory with the size class distributions, things that we dreamt about in the past. So for that stand situation before, where I just had quadratic mean diameter and gross vegetable volume, which 2 weeks ago I was thrilled at. Today, I'm pretty excited because now I have a volume distribution and I have a size class distribution in terms of stem size. We also have the ability, and this is kind of where these two products come together. We heard that LiDAR doesn't give you species. Well, it really doesn't. You need that imagery piece. And so we're using the line work of traditional inventory approaches, whether soft copy, heads-up digitizing, or whether you're stereoscope digitizing, that have delineated a land or delineated a stand on the ground and attributed species composition to it. We use that information to know which models to apply. So if we're crossing stand boundaries, we basically have the ability to say, okay, well, in this block that you harvested, you have jack pine and spruce and aspen or whatever the model types that we're applying here, and give that different distinct distributions. Is this species level? No. Because we're basically looking at jack pine dominated models, spruce dominated models, mixed wood models. If it's a mixed wood model, it's a mix of everything. So it's not really species, but it does give the mill operators an idea of what is going to potentially come from that block when they harvest it. Now, we say that LiDAR doesn't do species classification, and one of the frustrations parts I have about the way we're applying these LiDAR models is that we are using that stand vector layer, which could be 100 hectares. They circled on the map and they said, you know what, that's jack pine 50%, that's white spruce 20%, I've already lost, what did I say, 60, 80, and 10, and 20% poplar. Well, where is it in the stand? So I say, well, that's generally what I call a jack pine stand. Like I said, it's a jack pine. I apply a jack pine model. So when I go 20 by 20 meters, 400 square meters through that stand, applying my model, all of a sudden I hit poplar. And if that poplar was a lot taller than my model building data, my estimate for that 400 square meter pocket of that stand suddenly is wrong. And so what we're looking at trying to use the LiDAR, and this is low density LiDAR data, to help us classify and predict whether I'm looking at a conifer pixel or a hardwood pixel. I dreamt that I could do better. Right now we're basically a conifer and hardwood. Generally, we're pretty impressed that we can do, with this low density LiDAR, about 80% getting conifer correct in the mix. So this is some work that we're pushing through right now to try to implement in terms of refining inventories down the road with the rest of the model. In terms of validation, because again, is this stuff real? So we had those 138 plots on the Romeo and Juliet, and this is the result, again, one-to-one lines of the model validation plots with the calibration models that were used. And you can see generally we're seeing the same trend, a little bit wider distribution around the one-to-one line. Density didn't behave as we thought it wouldn't. It didn't. There was an issue with trying to predict the number of trees this way on the Romeo and Juliet forest, but the other ones worked reasonably well. Another level of validation, and I call this one sort of block level indication, is on the left-hand side, we're looking at what went into our sustainable wood supply modeling. This was the plan block for harvest. On the right-hand side, in the green areas, is what was really cut. Well, if you look at putting, say, the quadratic mean diameter, all of a sudden, you can see that what they really harvested was the larger trees. So this is the kind of a retrospective. We're looking back at what happened. The idea is if you had this raster layer available to you now, you could actually design your harvest allocations to meet the requirements you have. Now somebody out there might be saying, well, now you're promoting high grading. I'm not promoting high grading because you would still have to go whatever in Alberta you have sort of your sustainability measures. But the reality is, if you were going to do this exact scenario, at least you would model in your sustainability models what's actually happening on the landscape versus what we said we were going to do. So I think there's a real... So this works whether you look at whether it's gross virtual volume, the diameter sort of lit up very quickly for you. Another level is looking at, well, what was the scaled results of from what the LiDAR predicted? So I have a few examples here. So this is a jack pine block, and I have to thank Tim Beck for providing this data to us. The inventory planned volume was about 4,700 cubic meters. The LiDAR predicted 7,500 cubic meters. They actually scaled 7,700 cubic meters. Of the 43 blocks we've had a chance to look with, we were basically within 5% of what they scaled. So I was a cloud nine. This is a real sort of validation, which is much better than plots. In terms of this whole block, how well we're doing. So then we moved on to another scenario. And this is the poplar one. So the inventory plan was about 10,000 cubic meters. LiDAR had a higher estimate of 13.2. The scale was 12.3. So the LiDAR was within 8% on this on block 125. And one of the things that started to twig in my mind was, why are we getting this difference? Because I do have t-shirts that says LiDAR never lies. If you could see in this imagery, we have targets for retention blocks, wildlife trees, and things of that nature. So they're actually left in standing trees. The LiDAR doesn't know that. The LiDAR said the estimate based on that structure is X. Okay, so that's a little bit of the discrepancy. And that followed through more even with the black spruce, because I just about lost it when I got these results. We were off by 25% in the black spruce. Well, it turns out that for some reason they had the ability that they didn't need to take any of the small black spruce in the harvesting at all. And they were doing what's called careful logging around advanced regeneration, which is basically with a feller buncher going up and doing strips and leaving residual strips to regenerate those cutover blocks. So all that material stayed in the forest. So with the net downs from that, we're basically back in line, within that 5% window. Very quickly, we're going to do a couple examples here. So does any of this matter? So what I did on the Romeo and Juliet forest is I picked 3 pretty similar stands. Basically, they're jack pine stands, they're jack pine black spruce stands, relatively the same height, the same stocking, same site quality in terms of site class 2, crown closure is about the same. And if we go to our normal yield table, which is sort of the way we do our wood supply in our stand level volume estimates, all three of those stands would be 162 cubic meters per hectare. Well, in the LiDAR world, there's some difference. That first stand, we're up about 196 plus or minus 15. The second stand is 277.4, and the third stand is 190. All different than 162. But we also have the ability to look at all those other ones. I threw a quadratic mean diameter on that picture. So we have 18 centimeter average diameter, 20 centimeter, and 18 again on that bottom information. So if you're trying to do block design and you've got a mill to feed for a certain dimension of product, or you needed to require the remaining of certain habitat characteristics, you have that level of information now spatially, which is the strength of these data sets, on the landscape. And the other ability we can do as well is provide that density distribution and the volume distribution and show how these two different stands, while they may be coded in the inventory the same, they offer different product potentials and different structure characteristics throughout the stand. So that's a huge step forward. Now, I'm going to very quickly, because I think I have enough time, just talk about this. And one of the questions when I got into the LiDAR game is that we were playing with very low density LiDAR. That stuff I just showed you for the Romeo was 0.5 hits per square meter, very low. And I thought, oh man, if we only had what those Scandinavians have, you know, if I was up at 30, we'd be just cooking. I could get those RMSEs down, you know, 2%. Life would be good. Well, we couldn't afford to fly 30 points per square meter, but we did fly 3 points per square meter. And one of the reasons I'm a really big proponent of this type of modeling approach for inventories is that low density LiDAR meets its needs. We want LiDAR to be operational. And if to put me back in Ontario again, I have no LiDAR. If I'm trying to convince a forest company or the province of Ontario to fly LiDAR, there's no use trying to make a business case for trying to fly 30 points per square meter. I need to be able to find what that threshold is for the appropriate LiDAR to meet my modeling requirements, my data requirements. And we basically looked at cross-tolerant hardwood stands, and so that birch poplar mix, those mixed wood situations, the white pine, red pine forest types, and again, boreal jack pine and boreal black spruce in this project. And the assumption is, and I believe it was, Andy was showing similar relationships today. We basically threw a high-dense LiDAR cloud high, about 3.2 points per square meter, and then we used sort of a published approach to decimation of that LiDAR cloud to represent less intense acquisition. So we brought it from 3 to 1.6, and we brought that down to 0.5. And that's what these diagrams are on the bottom. Then if you look at sort of some of those LiDAR predictors that we talked about before, the P10s or the MAX and P90 and P80, those heights, those different canopy metrics, remember, we're trying to describe a line. Whether I have 1 point at that spot on the line or I have 5 points on that spot on the line, I still get that point on the line. And so this is trying to describe that. So these are the different levels of intensities. The darker is the 3 points, and 1.6, the orange is the 0.5. And you can see, generally, I can still recover that same shape of that statistical distribution for all the fours. Where it does change sometimes is at the tails. So over here, because I had less dense LiDAR, I didn't hit the tallest part that the 3-point data did. So you can see that I'm missing a whole bar up here in this height class. Long story short, let's just look at jack pine and black spruce. And so what this is we built models based on the decimated LiDAR data sets. So I'm looking at the RMSEs for these different LiDAR predictors. And let's look at quadratic mean diameter. So you can see my RMSEs for 3 was about 1.5. For half that, 1.6 points per square meter, 1.4. And for that lower density, it was at 1.6. This is percent RMSE on the bottom. And you can look across that number. And there's no statistical difference from 3 to 0.5 in terms of the density. So the LiDAR data that we operationally fly, which is around 1 right now, is flying out. There's no advantage for doing this type of modeling and these forest conditions that we sampled to go up to 3 or higher. We don't get any bigger bang for our buck. Now the good news for you, of course, is that here, oh sorry, if you're interested in this was just accepted in remote sensing that's coming out hopefully shortly. In Alberta, a prototype was done with your exact data in 2008. So I have permission from Kevin and permission from the folks here in Alberta to show some of the results of this. And so this was taking some of your data and actually developing from some of the provincial plots that are here, developing models for volume, basal area, and diameter, a few of those ones up here, and actually producing the raster surfaces. So please, what I'm telling you, worked in Ontario, what Chris has shown in terms of his work in Nova Scotia and elsewhere, what Andy's talked about in the States, those approaches will work here. They have worked here. I keep pointing, you don't see what I'm pointing at. They do work here. Those relationships are sound, and you can do it. The last piece of what I want to talk about today is trying to put this all in the user's hands, because it doesn't make any sense to have all that LiDAR data sitting there as point clouds or digital surface models, digital elevation models, and people can't use it to make better decisions. So in working with Lim Geomatics, Tecterra, who provided a chunk of funding to this, the Canadian Wood Fiber Centre, who also supported, and the M&R from in-kind trying to help shape the tool, we developed a web-based application that can show to people that anybody can use the products of this. And so what we have is this advanced forest resource inventory decision support system that we call AFRIDS. And I'm going to walk you through just some screen captures of this software. And if you do see a use for this software, the person to talk to is Kevin Lim at limgeomatics.com, and he can set you up with some more information. But this software will be hitting the market shortly. So here we have, this is basically running across the internet, or it can be on a desktop machine. It doesn't have to be a web-based application. All your privacy was web-based, so you can have multiple users logging in. And basically what you have the ability to do in some of the things. So if you have imagery, you can load imagery in. This is the roaming on the left forest we're looking again. I can turn on whatever shape files I want to throw up into the system. So here I have added the water polys and the road layers. I can zoom into an area. I can add the dam to that product as well. I can select the forest attribute that I want to choose. So we talked about all the ones we modeled, the PA, the volume, quadratic mean diameter, and so on. And so what I picked here, I picked the quadratic mean diameter. So now I have that raster available. Again, in this particular case, would be online across the web. And I can do a whole bunch of different things with that now. So let's zoom in again, and we can look at a little bit closer at that 20 by 20 meter resolution of our quadratic mean diameter for those different cells. I can go to some of the tools we have, and you can bring in, if you wish, the inventory that you have for that area. Because we tend to still, this is the base fabric that we do all our planning with, and using block design. You can overlay that in here. You can point to it and get your sort of your inventory information, something like an I information type toolbar. You can also, if you have allocations or something you've already designed, you can bring in your own shape files already, so you can load whatever you want. You can export back out of here in terms of shape files. You can also export all the things I'm going to show you as tabulated reports. You can also use the raster surface to design, say, block design. So if you want to come in and try to design where your harvest block is, because I have all these different inventory attributes at my fingertips, I can basically take the tool and I can draw the block that I want to harvest. I can then edit that. You know, if we have an area of concern, a stick nest, or whatever, you have to put a donut in your block. You can basically add that quickly. You can shape it. You can cut off that piece of the block. So basic sort of editing tool functionality exists within this particular tool. You can add a portion to it. And then you can go and basically ask the software to go and hit, in this case, that server box sitting in Lim's office, probably in his closet. You can basically say, give me a summary for whatever inventory metrics I'm after. And so you can use that checkbox, basically pick whether you want heights or whatever summarized. You also have the opportunity to select whether you want the confidence interval was calculated or not. And so the way it goes, you pick what you want, and what you get out is this basic box for this particular block. So you have your estimate of your prediction of your average height is 15 meters plus or minus 0.2. You know, your quad mean diameter 17.9 plus or minus 0.4 centimeters. a volume of 154 plus or minus 5.78. You could do multiple stands at once, or multiple blocks at once, and actually you can do a total as well. So it'll keep track of that. So down the left-hand side, you basically have tabs showing the statistics for each particular block, and you can go in and edit those or whatever. This pie chart basically gives you an idea of the distribution of the species that are involved in the block. So here in this particular one, 45 hectares of that 92 hectares is actually in Black Spruce forest. So we're really excited about this tool because, again, it gets that LiDAR and the inventory rasters that are often, disparate type layers that are sitting on a computer, actually in the hands of people to make some decisions. The other piece that's just going to be coming online very shortly is that diameter distribution piece. So now we'll be able to click another option on that list and populate these bar charts. We'll show you that volume distribution by 2 centimeter size class, or your diameter distribution. And again, at the top, you can see that you can export Excel summaries of tabular values as well as the shape files. If you actually create blocks on here, you want to export shape files out for Esri. That wrapped around. But Alberta is so lucky. I think that you have, it's just like a panacea. You're going to get more and more excited every time you try to see, can I get this from LiDAR data? And I am amazed what we're able to do. And I think some of the stuff that Andy showed before lunch, trying to get to some of those lower stand attributes, like coarse woody debris. Can you imagine? Trying to estimate some of that stuff. That's pretty amazing. There's definitely a whole opportunity of using DEM grids. So you have this great quality, high resolution DEM. Use some of the tools that are out there for things like predictive land classification. Do some flood modeling type applications. Hazard mapping, looking at slopes. We had to talk about that yesterday. I'm involved in a project in Ontario where they had these LiDAR clays in the Pembroke area, and there's a big push for housing subdivision, and we're faced with the saying, well, no, there was a big slide around that area in 2009, and we don't know the extent of it. So we've flown LiDAR there to try to characterize where are the areas that have to hold municipal construction away from for safety. Infrastructure development, another use for LiDAR. Predictive hydrology, we talked a bit about that, I wish I had more time. We found very good use in the forest industry of the predictive hydrology. So some of the things that we talked about yesterday in terms of the water modeling that Paul Mark, that the Jay is doing here for Alberta is phenomenal. And the results, numbers where the forest industry is finding that even a 5-meter DEM product, they're seeing that 85% of the time, unmapped streams that are now on a predicted stream layer. So ones that weren't available when they're trying to do their harvest block design, they're finding 85% of them within 30 meters of where the map's set in. That's pretty phenomenal. That's a lot of heads-up information and huge cost savings if the folks that are trying to do the layout know that they're going to need culverts. They can have that material set up and ready and permits in place to put them in. So the forest road construction, again, is another thing. You have a data set with no level of confidence that it can be scaled to meet multiple objectives. So there's actually a known quality about your digital elevation model products and standards about how the LiDAR was to be acquired. Opportunity to develop scalable inventory information. To try to tie, I think really importantly, strategic and operational planning together, instead of them being very separate. Strategic, high level, allocating wood, that, yeah, the inventory says it's on the land base, but operationally, trying to find and access it's a different thing. So actually trying to put those two modeling things together. Habitat modeling, LiDAR measures structure, vertical structure. That's what habitat is. It's basically structure. All the things we talked about today didn't require age. The biggest issue I have with age is that we can't look at a photo and measure age. All these predictions were basically measuring the structure, laying that structure from the LiDAR to the metric that we're trying to actually have. A lot of our issues that I see in terms of the difference between what the planned volumes were and the scaled volumes in the 10-back is because if the age was off by 40 years, the site quality estimate was off and went to the wrong yield curve. So if I would love to have sort of the LiDAR inventory to provide the fundamentals for yield curves, and I would like to have site productivity, which is always that age-height pair, have more of an ecological land classification approach to say, well, these are younger sites, these are more productive, these are my better sites, they're going to grow at this rate, versus microbial, maybe organic sites for another species, and things like that. But that's, that's my little role. I'm not allowed to mention that. Better planned and delivered harvest operations, no surprises. One of the things we're hearing from the company is that the estimates, the predictions that we made on the Romeo Millette forest, they're basically doing their payment now to their contractors. So if Block X says there's going to be 200,000 cubic meters to cut, the contractor's paid in the office for that amount. Done deal. They are so committed now after playing with the raster surfaces. If they have the quadratic mean diameter and they say that the average size is going to be 12 centimeters, they've walked enough of the stands now with the predictions in hand to have confidence that that's what they're going to get. So we're really impressed with that. Maximizing value. So from the industrial side, this is kind of where the Canadian Wood Fiber Centre, and I can't thank them enough for their partnership and their support financially and also with their expertise in this project, is the whole idea of getting the right mill getting the right wood to the right mill at the cheapest cost. We have a spatial inventory. We know the sizes that we expect to be out there. We can plan to make sure that if we're going to harvest block X, that we know that the wood for block X would be suitable to go to mill Y, versus having it go into the wrong mill and missing the opportunity to maximize the value. I work with a great forester named Dave Dugal. He's just recently retired. His favorite saying was, "Don't be afraid." And don't be afraid to try LiDAR data. Try to push LiDAR data. Move beyond the DEMS. The DEMS are great. They're going to help you in so many different ways. Look at those derivatives that are possible. But don't be afraid to try to work with the point cloud data. There are expertise within the government. There's expertise within the private consultant world that you can bring on board to do this type of work and or learn yourself. And I think if you look at that LiDAR point cloud, you'll be able to form some better decision. Thank you.